All right, we're coming down the home stretch here. We have problem number 11. Okay, and so just as a kind of a word of warning as we go through these, there are going to be a few problems for this last video that are on the actual unit review, but that I'm going to eliminate and we're not going to talk about, and you are not responsible to be able to do because in some cases they're overly complicated and we don't want to have to worry about that. Okay, so just I'll point them out as we go, but just keep that in mind. There's going to be some that I skip. Okay, so problem number 11 is asking us to express this in simplest form, which really just means do the division that they're asking us to do. Okay, and then after we're done, we need to state all relevant domain restrictions. Okay, so just as a reminder about how to divide, and on the next problem, how to multiply. Okay, whenever we're doing multiplication and division, we are going to factor everything, every numerator and every denominator that we can. We are going to look at all of the factors in the numerator and all of the factors in the denominator, and we are going to try to cancel anything that cancels. Okay, and then we're just going to gather up all the parts at the end in a multiplication problem, okay, and we're going to put them in our answer, and it's entirely okay to leave your answer in an unsimplified factored form for our purposes. Okay, so we're going to go through and factor each of these. Okay, we have one extra little thing about division, but we'll talk about that when we get there. So let's start off 6x squared plus x minus 15. Okay, this is again an AC factoring problem. It looks like you have a negative 90 and a 1, right? So you can go through and find that pair of numbers, right? I'm just going to give you the factored form, which is a 2x minus 3, okay, and a 3x plus 5, okay? And these will factor. Again, you can go through and do all the factoring and try to find that. The denominator here is a difference of two perfect squares, so I'm going to say that this is 2x plus 5 and 2x minus 5. Okay, and I'm going to do the same thing for the other one. So here's where things get a little different. Okay, division means multiplying by the reciprocal. So again, let me give you a simple example of that. If I had something like 2/3 divided by 7/9, okay, and I asked you to divide this problem, we wouldn't actually do this problem. We would take the division, turn it into a multiplication. We would take only the second fraction, and we would flip it over, okay, and then we would perform a multiplication problem. So that's what we're going to do with our fractions as well. I'm going to turn this into multiplication, and then I'm going to flip over my second fraction. So this I'm going to factor by noticing that it has a GCF of 8, okay? And I'm going to factor out that 8, okay? But when I put that answer in my new expression that I'm writing here, I'm going to put it in the denominator because I'm flipping as I go. So this has 8 times, well, it looks like I'm going to have a 2 and a 3 left, so this is going to be 2x minus 3, okay? And again, I can just check that's 16x and that's 24. That's what I started with. All right, and I'm going to do the same thing. This denominator has a GCF of 4. So I'm going to put the 4 out here, but it's going in the numerator now. And it looks like I'm left with a 2x plus 5. Okay, so again, I'm just checking that's 8x plus 20. That's what I started with. Good. That's what I was looking for. Okay, so let me get rid of this problem. So now that everything is all factored, we're going to cancel anything that cancels. So here's what I see. I see a 2x plus 5. And I see a 2x plus 5, okay, and I see a 2x minus 3, and I see a 2x minus 3, okay. I also see a fraction right here, 4/8, so I can divide both of these by 4 and turn this into a 1/2. So it looks like the only thing that's left over in the numerator is, well, 1 times 3x plus 5 is just 3x plus 5, okay, and 2x minus 5 and a 2, which, again, entirely okay to just leave it in its factored form, but if you want to call that 4x minus 10, you are more than welcome. It's just not necessary. So this is my answer. Okay, that is the simplest form of this division problem. Okay, we have one more part to this, and that's saying state all relevant domain restrictions. So here's where we have to be a little bit careful. I'm going to look at my denominator here, okay, and say 2x plus 5 and 2x minus 5. They are each going to give me domain restrictions, which means I want to know when was 2x plus 5 going to be equal to 0. So I'm going to just do one of these for you. When is this equal to 0? Okay, well, it looks like if I subtract 5, that's negative 5, and then I divide by 2, I get negative 5/2. So I can do that with this one as well, and I'm going to get positive 5/2. So I'm going to say x is not allowed to be equal to, let's make a list, negative 5/2, okay, positive 5/2. So I'm going to just write that one as well. You can also write this as plus or minus 5/2. Okay, I can do the same thing here, and I can say, well, 8. Don't worry about the 8. That doesn't have any variables in it. But 2x minus 3 is going to give me a positive 3/2. That's a bad value. Okay, here's where we got to be careful. And for this problem, it's not going to contribute anything new. In my original problem, 8x plus 20 was my denominator. That number now is in the numerator here, so this 2x plus 5 is also going to contribute a domain restriction because it used to be a denominator. In this case, when I solve 2x plus 5, we just did that. It gives me negative 5 over 2. I've already listed that one. But we have to be careful to just check and make sure that there's nothing left in the numerator here as well, because that could possibly give us a restriction. So here's my kind of complete answer, okay, with the domain restrictions. I'm saying 3x plus 5 over 2 times 2x minus 5 is my solution. That's my simplest form. And I've stated all of the relevant domain restrictions. Okay, so problem number 12 is the same thing. We still have to factor. The difference is because this one has multiplication, I don't need to do that reciprocal step. I don't need to flip anything. Okay, so here are your factors. Again, we're gonna go through this, and again, I'll let you do the factoring in order to figure out how to get this. Okay, but the first fraction turns into, it looks like 2x minus 9, okay, and 4x minus 3, right? And so this is a fairly big number, right? When you do your AC factoring here, it's pretty big, okay? You're going to get a number that's a couple hundred, right? But it's just going to take a little bit of time, so don't worry that if it takes you a little bit of time to find out how to factor this, okay? The bottom, it looks like factors twice, so again, I'll show you this off to the side. The first thing I'm going to do is I'm going to GCF an x out, okay? And then I'm going to factor x squared minus 81 again into x plus 9 and x minus 9, okay? So this factors twice. Okay? So now I'm going to do the same thing here. This looks like it factors twice as well. So let's do the same thing here. So just so as not to confuse you, I will get rid of the other one. Okay, I'm going to pull out a GCF of 3x. Okay, and then it looks like I'm left with x squared minus 9. Okay, and then this factors again into x plus 3x minus 3. Again, let me point this out. I am not going to put this in the denominator now because I'm not flipping, because I started with multiplication. So it looks like 3x, x plus 3, and x minus 3. Okay. Let's get rid of this extra work here that we did. Okay, fix my problem. Right, all right, so that's a really bad 3, but we're going to go with it. Okay, my last problem, I'm seeing it's a little backwards, so I see there's a 3 involved with each of these, but I'm actually going to pull negative 3. And the reason I'm going to do that is because it's going to turn this into positive 2, okay, and it's going to turn this into a positive 3, right? So this, I'm sorry, a positive 9, okay, so plus 9. I'm sorry, minus 9. Okay, so this is going to turn it into a minus 9. Right, and I did that because I noticed that I had something up here that was probably going to work out. Right, so I kind of just thought ahead a little bit and said, okay, if I pull out a negative sign, it'll flip it and make it look like this one as well. So you might have to like first pull out a 3 and then notice that things are backwards and switch it. Right, but I just kind of did all that together. All right, so let's do our canceling. Everything's factored. I'm seeing 2x minus 9 and a 2x minus 9. I'm seeing no x plus 9s in the numerator. I'm seeing no x plus 3 or x minus 3s in the denominator. Here's what I see. I see an x, and I see a 3, and a 3, and that looks like it's it, right? That's all I was able to cancel. So I'm going to now gather up what's left over. I have 3 factors in the numerator. Okay, I have 4x minus 3. I have x plus 3. And I have x minus 3. Okay. And in the denominator, I have x plus 9 and x minus 9. Okay. And I have this negative sign, right? So we have to figure out how to deal with this negative sign, right? This right here is kind of floating around still, right? And so I'm going to actually take it. I could put it here, right? And that would be fine, right? But usually negatives in the denominators are not helpful. So I can actually place it up here as well. So negative on the top, I can place that anywhere I want. If I wanted to, I can make the whole fraction negative, and that would be fine too, right? So we had lots of options there. All right, so now we have to do the domain restrictions. So again, no, not allowed to have any zeros in the denominator. So I'm saying x is a factor. So let's say x is not allowed to be equal to 0. Okay. X plus 9 is not allowed to be equal to 0, so that's going to be negative 9 and positive 9. So I'm actually going to write this one as plus or minus 9, just to show you a little different strategy. Okay, and then it looks like the negative 3, it doesn't have a variable, so that doesn't contribute at all. And this one's going to give me a 9 over 2. So I'm going to say 9 over 2, okay, is bad. Okay, and in this case, I am not going to consider these numerator values because they were never in the denominator of anything. They were in the numerator to start. They are still in the numerator, so they are allowed to be 0. They will not give us an issue. So I would say my entire final answer is this big expression, simple form, okay, with my domain restrictions. Okay, so That's our multiplication and division. So here's our first skip. We are going to skip problem number 13. We're going to go right to problem number 14, which is asking us about average rate of change over an interval in a couple of different situations. So in letter A, they're giving us a table of values. They're saying this table of values came from some function g of x, and they want to know the average rate of change over this interval. So if you remember, average rate of change is really kind of like slope when you talked about linear equations, where we're going to say subtract the x's, which my interval is telling me about the x's. So I'm going to say -4 minus 2. And then to get my y values, the output values that went with those x's, I'm going to look at my table and say, okay, for an x value of -4, I got an output value of 4. So right above the -4, I'm going to put a 4. And I'm going to do the same thing with the second one. It had a 2, right? 2, not -2. It had a 2, and that contributed a 7. So I'm going to subtract those as well. So it looks like I get a -3 on the top, and I get a -6 in the denominator, and that simplifies to 1/2. So my average rate of change over this interval for g of x is 1/2. That's part A. Okay. Part B is asking me to do an average rate of change as well over the same interval, except this time they're not generating a table for me. They're just saying, here's the function. F of x is the square root of -2x plus 8. So we're still going to say, for our problem, that the denominator is, let's subtract, okay, the interval values, the -4 and the 2. Okay. Now here's where it gets different. We can't just look at a table. We don't know what comes out of the function for -4 because they didn't make the table for us. So we actually just need to say, well, what is f of -4? What happens to this function when I plug in -4? Well, that's going to be -2 times -4, okay, plus 8. Well, -2 times -4 is 8. 8 plus 8 is 16. So this is really the square root of 16. So when I plug in a -4, I get back the square root of 16, which is 4. So I'm going to put a 4 there. Okay. So let's do the same thing with 2. I'm going to do the same thing. Let's find out what f of 2 is. So I'm going to say the square root of -2 times 2 plus 8. -2 times 2, well, that is -4, and -4 plus 8 is the square root of 4. So I simplified my radical. The square root of 4 is 2. So in this case, I'm going to subtract 2. So this says 4 minus 2 on the top, which is 2 over -6, right? And I can simplify that a little bit more, and I'm going to squeeze it in right here. It says -1/3, right? This is my simplified average rate of change for f of x. Okay, so now the last part is saying compare A and B and determine which one has the greater average rate of change, and by how much. Okay, so here's what we need to remember. When we're thinking about average rate of change, the 1/2 and the 1/3 are the average rate of change. In this case, the negative sign, what that's really contributing is direction. It's telling us that for this interval between -4 and 2, the graph is traveling down, right? It's kind of going on a downward slope. So I'm going to really just say that 1/2 is a bigger fraction than 1/3, and if you don't believe me, I'm going to try to compare 1/2 and 1/3 and wonder what's the inequality in between them. In order for me to do that, I'm going to put them both into the same denominator, which is sixths. So this is 3/6 and this is 2/6, and it's obvious that 3/6 is greater than 2/6. So I'm going to say in this case that 1/2, which is g of x, is the greater average rate of change because 3/6 is greater than 2/6. It's asking us by how much. We are going to say by, well, if I do 3/6 minus 2/6, okay, it looks like it is 1/6 larger. So I'm going to say that the average rate of change of g of x is 1/6 larger than f of x. Okay, so that's using average rate of change, comparing them, and being able to say that one is larger than the other. All right, so let's talk about problem number 15. Okay, so problem number 15, I'm going to skip something as well. I'm going to skip 15a, and we're going to go right to 15. All right, so for problem number 15, we have an expression we're being asked to simplify radical expressions. And if you notice in this problem that one of the radicals is a square root, and one of the radicals is a cube root. And we said at the beginning that you cannot multiply together radicals that have different index numbers. And so the best that we can do in this problem is to simplify the square root, simplify the cube root, and then if anything on the outside can combine, we're going to do that as well. So here's the way that this one's going to look. All right, so we're going to go through and we are going to just simplify the square root of 96 x to the third y to the third. Okay, so for this particular problem, the square root of 96 can be broken up into 16 times 6. Okay, so that's my perfect square, 16. And remember, we said for numbers that are indexed 2, we want multiples of 2. So I'm going to turn this into x squared and x. And I'm going to do the same thing with y. I'm going to turn it into y to the 6th and another y. Right? So I did that because this simplifies to 4. Okay, this simplifies, remember, just divide the exponent with the index, that little 2 that's hiding out here. So this is just x to the 1. And I'm going to do the same thing here. This is 6 divided by 2. This is y to the 3rd. And then I'm going to gather up. It looks like 6 and x and y have to go back under the radical. Okay, I'm going to do the same thing for the second problem. So I'm going to use a different color so we can see that it's different. Okay, 1029 is a pretty big number. So for this particular problem, you're going to have to go through and say, okay, 2 to the 3rd, 3 to the 3rd, oops, 3 to the 3rd. Okay, and you're going to have to actually list them out and say, okay, 2 to the 3rd, it looks like is 8. Is 8 a factor of 1029? In this case, no, it's not. You're going to check 27. Is 27 a factor of 1029? If you check, no, it's not. 4 to the 3rd. Is 4 times 4 times 4? Okay, 4 times 4 is 16 times another 4 is 64. Is 64 a factor of 1029? No, it's not. Okay, we're going to check 5. 5 to the 3rd is 5 times 5 times 5. That's 125. Is 125 a factor of 1029? No, it's not. And I'm going to continue this. 6 to the 3rd, okay, is 6 times 6 times 6, which I believe is 216. No, it's not. 7 to the 3rd is 343. Is 343 a factor of 1029? Yes, it is. So that took some work. And that's sometimes the work that you're going to have to do once you get to these larger values. And I'm going to say in this case, this is 343. Okay, times 3. And that's how I'm going to have to simplify that 1029. This took some work. It took some effort. We had to go through and find the value, right? And that's sometimes the work that you have to do, right? So I'm going to keep going with this. X to the 16th, I'm going to break this up into the cube root of x to the 15th because remember, now I'm looking for multiples of 3 because my index is 3. And I'm going to say I have one more x because I had 16 total. Y squared I can't do anything with because it is not a multiple of 3 and I cannot break it up smaller into a smaller value that is a multiple of 3. So I'm just going to leave that one alone. Alright, so here's how this one simplifies. I can cube root 343. I can cube root x to the 15th, and that's it. So I'm going to turn this into a 7, okay, times 7. Right, that's the cube root of 343. And I'm going to cube root x to the 15th by saying 15 divided by 3. It looks like I have x to the 5th on the outside. And then I'm going to gather up everything else that's left, 3xy squared, and I'm going to leave that alone. Okay, so that's pretty much done. We simplified each of the radicals. Here's our last little kind of cleanup. Anything that's outside of the radical is now, it's not exclusive to that radical anymore. They're just regular old numbers. This says 4 times 7. I can put those together and get a 28. X times x to the 5th is x to the 6th. Y to the 3rd, I have nothing, no y's on the outside to combine that with, so I'm going to leave it as y to the 3rd. And then the other two parts I'm just going to kind of bring along, 6xy and the cube root of 3xy squared. And I would say this is as simple as I can make this because I cannot combine the square root and the cube root, right? And but all the stuff on the outside I was able to put together and do something with, okay? So problem C, 15C, right? We have to be careful. The 2 and the 4 that are on the outside of 15C, those ones are not index numbers. Those are regular numbers that can be multiplied. So I'm going to do the same thing. I'm going to simplify each of the radicals separately. Okay, and I'm going to break out anything I can break out, and then we're going to see where we're at when we clean up. So it looks like 28, right? So let's get, so the 2's kind of sitting there. 28 is 4 times 7. Okay, x to the 5th is x to the 4th and an additional x. Okay, and then y to the 12th I'm not going to break up because it's already a multiple of 2, and I can already square root that one. Okay, so I'm going to do the same thing with the second one. This is times 4. Okay, 16 is made up of, 60 is made up, I believe that is 15 times 4, right? 15 times 4 does give me 60, and so I'm going to use that. Okay, so I'm going to break this up into the square root of 4 and the square root of 15. Okay, I'm going to say x squared and x. Okay, I'm going to leave the y alone because that can't square root. And I'm going to leave the z alone because they do square root. I can square root all 14 of those z's because it is a multiple of 2. So again, let's go through and simplify. 4 simplifies, x to the 4th simplifies, y to the 12th simplifies. So this really says 2 times 2, right? So let's not be really careful and explain this. The square root of 4 is 2, and then I can multiply that with the one that's already there and get a 4, okay, x squared and y to the 6th, okay, and then I'm going to put together the 7 and the x. I said 7, but I wrote x. Let's fix that. 7 and the x, okay, and I'm going to do the same thing with the second radical. This is going to become the 4, and then I multiply square root another 2, so this is 4 times 2, which is 8, okay, so that's square rooted. Okay, and then I have x squared. The square root of x squared is just x. Right? X doesn't square root, y doesn't square root, but these z's do. That's 7 z's on the outside. Okay, so now it looks like under this radical I have the 15. Okay, I have an x and a y. So here's where things get a little different than our last problem. Right? I'm going to say 8 times 4 is 32. X squared times x is x to the 3rd. Y to the 6th, I have no y's over here, so I'm going to bring that along. That didn't change. And I have this z to the 7th in the second one, which I can also bring along into the combined version. Here's the difference. Now these two radicals, the square root of 7x and the square root of 15xy, they are both the same index. They are both index 2 regular old square root, so I can multiply those problems together. Right? So I'm going to say 7 times 15. Again, if this was like a no calculator section, we'd say it looks like 105. So I have the square root of 105 x squared y, right? The x times the x, and then the y kind of came along. And so now this created a little bit more work for us, right? Which is unfortunate, but we have to do it. I can break out this x squared as well, just like we did up here with this x squared. So I'm going to have I'm going to have an extra x kind of jump out of the radical and combine with these ones, and it's going to become 32x to the 4th, y to the 6th, z to the 7th, and now I have no more x on the inside. So because when I put together these two radicals, I got another multiple of 2, I was able to do a little bit more combining. Okay, so this is now complete. So just for the sake of time, I am not going to do D because D is very similar to what we just did in letter B. If you notice, an index of 2 and an index of 3. Right, so simplify your radicals, combine what you can combine, and you are finished with that problem. Okay, so let's finish up with our graph. So again, I skipped problem number 16A. I did not do it. Okay, we are just going to focus on 16B because they're very similar, and you're going to see that this one is a little bit more straightforward for us. So they're first asking us, what is the parent function? So your job is to be able to look at this graph, look at its shape, and know what type of function it was, right? So like we know, for example, that y equals x, which we call linear functions, those ones look like lines. And we know that y equals x squared, all of those ones look like parabolas, right? And we know that y equals x cubed, all of those ones look like a turn, right, type of function. So this one is none of those, right? So we're not going to use any of those. We know absolute value looks like V shapes. Doesn't look like that. So we're kind of running out of options. The only one that we haven't talked about is the one that it actually is, and that is the square root of x. Right? So this is a square root function. That's what this parent function is modeling, right? This parent function is the square root of x. Okay? And so now they're asking us to identify how did we change this parent function to get the new one, right? So let's first talk about kind of just listing them, right? The translations, right? What did we do to move this one? So my original starting point was at the origin. It looks like I moved 1, 2, 3 units to the right. So I'm going to say it was a right by 3, okay? And I went up by 2, okay? But if I did that, my graph would kind of be here. It would be in the right location, but it would be going that way. And it's not going that way. It's actually going to the left, not the right. So we have to figure out, well, how do I change that? Well, so let's describe it in words first. Let me get rid of this. Okay, it looks like I'm reflecting it to the left, and that would be over the y-axis, right? So to go from left to right, I'd have to reflect over this. So I'm going to say that. Okay, let me fix this. This is right. Okay, and then I'm going to say reflection. Right, a left to right reflection would be over the y-axis. Okay, so now we got to figure out which A, B, C, D values. So remember, our functions have A, B, C, D in them. They all do these transformations. So a move left and right, that is a C transformation. A move up and down, that is a D transformation. Okay, and a reflection over the y-axis is a B transformation just by making it negative. Okay, so let's figure out kind of how this is going to work. So I'm going to start off with my square root of x. And I'm going to give myself a little space because we're going to put some stuff inside there. So let's do the easy one. An up 2 would be a plus 2 on the outside. Okay. And a right by 3 would be a positive 3 move. So I'm going to say this is x minus 3. Remember, this is opposite of what you'd see. Okay. So I'm going to put that in parentheses. Okay. And then a reflection over the y-axis would just be changing the sign of b. So I'm going to put a minus sign there. So this is the function that we're modeling in our problem, right? And so now they're asking us, well, what are b plus c plus d? Well, my b value is -1, my c value is 3, my d value is 2, so I'm going to subtract 2. So -1 plus 3, that is 2, 2 minus 2 is 0, right? So they were just asking us to now look at our function, pull the b, c, and d values out of the problem, right? And then once we've done that, we can just add and subtract them as they've